Stand at the base of a volcano in your mind, close enough to feel the heat rolling off the vent, close enough to watch the rock glow and the air shimmer above it, and picture what actually kills people in a disaster like this. Lava, probably. Fire, maybe, racing down a slope faster than anyone could outrun it. You'd be picturing the wrong danger entirely. The thing that ends up doing the real damage doesn't come from the mountain at all. It comes from the sky, months later, thousands of miles away, and it isn't hot. It's cold. Here's the mechanism underneath almost every volcanic disaster that has actually reshaped human history, going back thousands of years. A large eruption doesn't just throw out ash and lava. It punches sulfur dioxide gas straight through the lower atmosphere and into the stratosphere, 10 miles up and higher, above where rain can ever wash it back down. Up there, that gas slowly reacts with water vapor and turns into a fine haze of sulfate particles, individually far too small to see. And that haze can circle the entire planet within just a few weeks on the stratospheric winds, sitting in place for a year or more because there's no rain up there to rinse it back out. Those particles don't burn anything. They do something quieter and, over time, far more damaging. They scatter incoming sunlight back into space before it ever reaches the ground, acting less like a fire and more like a dimmer switch turned down on the entire planet at once. You don't have to take that on faith. In April of 1815, Mount Tambora on the Indonesian island of Sumbawa produced the largest eruption in at least 1,300 years, throwing an estimated 10 billion tons of material into the atmosphere over 10 days. The following year, 1816, is remembered in New England and across Europe as the year without a summer. Snow fell in June. Frost killed crops in July. Global temperatures dropped by somewhere between 0.4 and a full degree Celsius, and in some regions, considerably more. The cooling and the crop failures that followed are blamed for well over 100,000 deaths worldwide, mostly from famine and disease rather than the eruption itself, and the year picked up a bleak nickname at the time, 1800, and froze to death. It's worth being honest here. Tambora didn't act alone. The eruption landed at the tail end of a centuries-long cold stretch called the Little Ice Age, and overlapped with an unusually quiet stretch of solar activity known as the Dalton minimum. The volcano didn't create the cold world of 1816 out of nothing. It took an already cold planet and shoved it further. A cleaner test case came almost 2 centuries later. When Mount Pinatubo erupted in the Philippines in June of 1991, it injected roughly 15 million tons of sulfur dioxide into the stratosphere. And this time, satellites were watching the entire event unfold in real time. For decades afterward, the textbook number was a global cooling of about 0.5 degrees Celsius, peaking roughly a year and a half after the eruption. Then, in 2024, a team of researchers went back through 43 years of continuous satellite temperature data with a more careful statistical model, separating the Pinatubo signal from long-term warming and natural year-to-year noise. Their revised figure came in smaller, closer to 0.2 of a degree, lasting a little over a year, not the 3 years some earlier estimates had assumed. The eruption still measurably cooled the planet. It just did less of it, for less time, than 3 decades of textbooks had been saying. Pinatubo's sulfate haze had other side effects too, ones that had nothing to do with temperature at all. It measurably thinned the ozone layer over the following 2 years, cutting tropical ozone levels by several percent, a reminder that a single eruption's atmospheric chemistry reaches further than just the thermometer. Now scale the question up. Earth has roughly 1,350 volcanoes considered potentially active today, and at any given moment, only around 20 of them are actually erupting. So what would happen if, somehow, all of them erupted together? You'd be combining hundreds of Tambora and Pinatubo-sized sulfur injections into the stratosphere simultaneously. A haze thick enough that the honest answer is nobody has run that exact model, because nothing like it has happened in the span of human record-keeping. But the individual eruptions we do have data for all point the same direction, not a hotter world. A darker, colder one, potentially for years, with global agriculture the first casualty long before anyone standing near a caldera would be. Even a single Tambora-class event dropped temperatures enough to fail harvests on the other side of the planet. A synchronized eruption of even a small fraction of Earth's active volcanoes would be stacking that same effect on top of itself, region after region, all at once. Here's where the science gets genuinely contested, not just uncertain. In 1993, geologists Michael Rampino and Stephen Self proposed that the eruption of the Toba supervolcano in Sumatra, roughly 74,000 years ago, triggered a volcanic winter severe enough to crash the entire human population down to a small surviving group. A genetic bottleneck still visible, they argued, in how little genetic diversity modern humans carry compared to other great apes. For years, it became one of the most widely repeated stories in human evolution. Then other researchers went looking for direct physical evidence of that volcanic winter, specifically in East Africa, where early human populations were living at the time. A study led by Christine Lane in 2013 examined ash-bearing sediment from Lake Malawi, over 4,000 miles from Toba itself, and found no trace of the severe, sustained cooling the theory required. Archaeological sites in India show stone tool traditions continuing across the Toba ash layer without an obvious gap, suggesting people there kept living, working, and surviving right through it. Geneticists studying the human family tree raised a separate problem entirely. The dates when human populations expanded again don't line up cleanly with the dates when a bottleneck should have started, which is exactly the kind of mismatch you'd expect if two unrelated events just happened to land near each other on a 100,000-year timescale. The genetic bottleneck in human history looks real. Whether Toba actually caused it remains, honestly, unresolved, a story that took hold not because it was proven, but because it was a good story that happened to fit a coincidence in timing. There's one more myth worth clearing up before the picture is complete, because it changes what the real threat even is. You've probably heard someone claim that volcanoes release more carbon dioxide than all of human industry combined. The United States Geological Survey has actually measured this directly, and it isn't close. Global volcanic activity adds up to less than 1% of the carbon dioxide that human activity releases every single year. By some estimates, humans outproduce every volcano on Earth combined by more than 100 times over. So if every one of those 1,350 volcanoes erupted at once, the greenhouse gas wouldn't be the story, even stacked up over years of continuous eruption. The haze blocking the sun would be, and it would arrive on a timescale of weeks, not the decades a slow buildup of CO2 would need to matter. The mountain that looks like it's trying to burn the world down would actually be trying, however briefly, to freeze it. So picture that volcano again, the heat on your face, the glow of the vent, the instinct to run from the thing that's obviously on fire. That's the part your senses were built to fear, and it's almost never the part that ends up mattering. The real damage shows up later, higher up, and colder than anything the mountain itself ever touched. Not fire raining down on the towns nearby, but sunlight quietly switched off over the whole planet, one sulfate particle at a time, for people who never saw the eruption at all.